Hello students, today we are going to see the oscillations and waves. The oscillations and waves, already we have studied these topics in your PUC level. What is oscillations? You would have seen many examples in our day-to-day life. That is oscillations of a simple pendulum, I think you would have seen in your school experiments, and oscillations of a vibrating stretched string, or the bridge which is oscillating due to the wind force. So these are some of the examples of oscillations. So under this oscillations topic, we are going to see some various subtopics. Let us say, what is simple harmonic motion? Mechanical simple harmonic oscillator, that is nothing but a simple pendulum. Free oscillations, damped oscillations, forced oscillations, resonance, sharpness of resonance, and Helmholtz resonator. These are the topics we are going to cover under this module. So what is oscillatory motion? The motion which is periodic in time, that is the motion that repeats itself in time. So if you take a simple pendulum, the pendulum is oscillating with a periodic motion, that is from any motion which is oscillating from its mean position will be considered as a periodic motion. I think you would have seen your wall clock which is in your grandfather house, or the wall clock which is there in the ancient days. So when you observe those wall clock, there will be a pendulum at the bottom of the wall clock which will be oscillating with a proper interval of time, that is one oscillation per 1 second. So there are some examples of oscillation, the power line oscillators when the wind blows in the past, or earthquake oscillation moves a building. So what is simple harmonic motion definition? Simple harmonic motion is defined as a motion which repeats itself at a regular interval of time. Or in other ways, if you want to speak with respect to the physics, simple harmonic motion is an oscillatory motion in which the force acting on the body is directly proportional to the displacement. What is that force acting on the body? That force will be called as a restoring force. So let us see what is restoring force in forthcoming slides. Let's discuss, there are some various examples of oscillating system. The oscillations of a simple pendulum, the swing of a pendulum of a wall clock. As I explained, in the olden days, there will be a pendulum at the bottom of the wall clock which will be swinging for a period of time. For each one swing, it will be considered as 1 second. Then oscillations of a balance wheel of a wristwatch. So the watch which is working based on the key, in which if you open and see, there will be a wheel which is rotating in a half a way. So that will be considered as an oscillation. Projection of a uniform circular motion and diameter, that I will explain later. Then vibrations of a prong of an ancient tuning fork. Vibration of a plucked string of a string instrument like violin and guitar. If you see violin or guitar, if you just disturb it with which is at the tension, then it will be oscillating and producing some sound. Similarly, the tuning fork, I think you would have done many experiments by using the tuning fork experiment by using sonometer. Okay, so these are all some of the examples of simple harmonic motion. Let us see the oscillations in detail. A boy is swinging from here to here. So when the boy is given with the force from this point, the boy tries to swing toward this direction and reaches the maximum height, and again it goes to the reverse direction. So from the point here to reaching here and once again reaching at the same point will be considered as a one oscillation. Okay, so this is considered as oscillation. Suppose let us compare the same swing with respect to the simple pendulum. So this point will be called as a equilibrium position, and this point will be termed as a maximum displacement. So suppose let us say I am going to apply some force to the pendulum along this direction. So what happens when I apply the force? When I apply the force, the velocity increases, the acceleration is also increases. Velocity increases, acceleration increases. So at the point of applying the force, the acceleration will be there. Then later on, acceleration will be keep on decreasing with respect to the displacement. When displacement increases, the acceleration will be decreasing to this point. So when it reaches at this point, the acceleration A becomes 0. When it reaches this point, the acceleration A becomes 0. At that point, the pendulum attained the maximum displacement. The pendulum attained the maximum displacement. When the pendulum attains the maximum displacement, there will be a restoring force which will be acting in the opposite direction of the pendulum, or opposite direction of the force in which it is applied. So the force which is applied in the opposite direction will be called as a restoring force. Will be called as a restoring force. Will be called as a restoring force. The restoring force always acts in the opposite direction of the accelerating body. So here at this point, the restoring force will be maximum. The restoring force will be, at this point, the restoring force will be maximum. So here when it keep on reducing, the restoring force reduces. At this point, the restoring force will be 0. Further, when it increases in the opposite direction, restoring force is also going to increase and reaches the maximum point or maximum value. So again, the pendulum is going to come back to the equilibrium position. This is how the restoring force plays a major role for this oscillating system. So whenever the oscillating system has a restoring force, that will be called as a simple harmonic motion. Got it? So let us discuss about what are all the conditions of the simple harmonic motion. Stable equilibrium position is required, as we discussed. So the position at the center point, that will be the stable equilibrium position. So if there is no stable equilibrium position, then the particular oscillating system is not considered as a simple harmonic motion. So no dissipation of energy. So this is the condition in which the pendulum is oscillating in a frictionless atmosphere. So there you can assume that the simple harmonic motion which do not dissipate any kind of energy at all. The third point, the acceleration must be opposite and proportional to the displacement. So this is what we have discussed just now. So there are some characteristics of the simple harmonic motion. Let us see one by one. The first characteristic is nothing but simple harmonic motion is a special case of periodic motion. What is the difference between periodic motion and simple harmonic motion? The clock, which is the needle rotates at a equal interval of time. Am I right? So for every 1 hour, the small needle is going to have one complete revolution. So 5 hours, 5 revolution. That is also a periodic motion, but it is not a simple harmonic motion. Why? It does not have any restoring force. That is the reason the simple harmonic motion, all periodic motion is not a simple harmonic motion. So there are some simpler motions which have the restoring force, or it oscillates with respect to the two extreme maximum amplitude, will be considered as a simple harmonic motion. That is point number 1. The point number 2, the simple harmonic motion system must have mass and hence inertia. Obviously, if there is no mass, there is no inertia, the object cannot move from its original position. So mass is required. The third point, the simple harmonic motion, constant restoring force always acts on the body. So as we discussed earlier, if there is no restoring force, the body will not come back to the equilibrium position. So restoring force is a foremost one to have a simple harmonic motion. Then the fourth point, the simple harmonic motion, the acceleration produced in the body due to the restoring force is directly proportional to the displacement of the body from its equilibrium. So we have seen in the last slide. In simple harmonic motion, the direction of acceleration and restoring force is opposite to the displacement. Yes, the simple harmonic motion is represented as x is equal to a sin omega t, where a is the amplitude and omega is the angular frequency. Now I am going to put this simple harmonic motion in the form of equation, mathematical equations. So what is the restoring force? Restoring force F is equal to minus ky, where this equation is called as a Hooke's law. Okay, so F is equal to minus ky. According to the Newton's second law, the force what we apply to the simple pendulum, so that is nothing but, suppose you consider this is my simple pendulum. In this pendulum I am going to apply the force to this side, so the pendulum is going to oscillate like this. So whatever the force I am giving to this simple pendulum, that will be F is equal to ma, mass into acceleration of the system. When I apply this force, the object is going to move towards this direction and the restoring force will be acting in the opposite direction. So restoring force F is equal to minus ky. Okay, so these two forces are equal in opposite direction. So ma is equal to minus ky, where acceleration a is equal to d square y by dx square. Right. So I am going to equate these two forces. M into d square y by dt square is equal to minus kx. This x or y, whatever it is there, it is going to represent the displacement of the system. It is going to represent the displacement of this particle along the x direction or y direction. Okay, so m into d square y by dt square is equal to minus kx. So I am going to bring this m towards the right hand side. So d square y by dt square is equal to minus k by m into y. Now I am going to write this equation in the form of second order differential equation. So d square y by dt square plus k by m into y is equal to 0. I am going to replace this, the coefficient of y, whatever the coefficient of y is there, I am going to replace it with the constant value omega square. So I am going to get d square y by dt square plus omega square y is equal to 0. So this is the second order differential equation. The solution for the second order differential equation is y is equal to a sin omega t, where a is the amplitude and omega t is the phase at a time t.